what in your mind is the most valuable idea on planet Earth at this moment in time?
Freedom of speech.
Ooh, ooh, very complicated.
And the concomitant freedom of thought and freedom to discuss and freedom to debate and freedom to problem solve as a group. Because if you don't have freedom of speech, this is like basically Jordan Peterson. But if you don't have freedom of speech, you can't do any of those things. You can't actually debate. You can't actually collectively solve problems if you will not tolerate dissenting opinions. So, see this?
Yep.
This is a satellite image of where I live. I actually live. I live right here. Okay. But this is the city of Palm Springs, California, right here. Here's Palm Springs Airport. And then there's all these other cities to the right. They extend. This is kind of a bunch of little cities in the desert. But this is right after the storms. Oh, look, do I have? Hang on a second here. Let's see.
Are those your satellite images? That's pretty high fidelity.
Yeah, right. So like, here's the day before. Actually, let me try and make this a little bigger. Here is the day before the storm, and then the day of the storm. It's all clouds, so you don't see anything. But then hang on a second. Yeah, so here's the day before the storm. Here's the map overlay. Okay. Anyway, here's the day before the storm, and then here's the day after the storm.
Wow.
So this doesn't cover, and here's some still remaining clouds. But like, look here. So before, after. Okay. This is a wash right here.
Is it like sedimentation? Does it just come down?
Yeah, this was just, there was a bunch of water that flowed here. It came and went, and it left a bunch of marks. This is kind of interesting too. Look at this. It happens. For better or for worse, there's a lot of windmills here, a lot of wind power. And again, before and after. Here's a wash right here. So up here, see this up here?
Yeah.
This is Interstate 10.
Okay.
This
wow.
They knocked out a bridge here. Okay, I believe. And also there's trouble around here. Anyway, so that's kind of interesting. All right, I'm gonna stop sharing.
Very interesting.
So wow. I did find there was no flooding where I was, other than some, the yard got wet.
That's really, really cool. But were there any deaths, or was everyone?
No, I don't think there was any. Even in the mountains where like there was like some trailers and stuff like that got, really wrecked. But no, I don't believe there was any deaths at all. No, it was nothing like. No, it wasn't a tragedy of that magnitude. It was just a severe weather. I mean, California has mudslides and fires and all this kind of stuff. It's just earthquakes.
The news was horrible about it. It seemed like,
yes, well, what is it? I mean, it's like bland news does not sell, right? So no, the news was horrible. But look, what was horrible was those fires in Lahaina. Those were horrible.
Yeah.
But this was not. This was, I mean, I'm sure some people have been kind of wrecked financially unless they have good insurance on their properties. But as far as I know, no one died. Yeah, well, but the news, look, what do? They go out on TikTok and Twitter and they're like, send us the worst video you can find. We'll pay you for it. So the one place where there's like water that's like flooding into the cars, like that's what you see. And that's what everybody sees. And so that's like, I don't want to minimize the impact it had on the people who were impacted, but as far as tragedies go, this is pretty lightweight. Now, it could have been worse. The storm had rather much dissipated by the time it got here. But and another thing is, by the way, getting into the whole climate thing, which we can do later, it's like hurricanes do hit the California coast. It doesn't happen very often, but they do. Okay, and people have short memories.
That they do. There's also this sort of over amplification thing, but no,
Yep.
I agree. So okay, so to get into it now, complete.
Fine. Oh, wait, no. We were missing one thing. I wanted to hear just a little bit about you, if we could start. I don't mean to kind of take the command here, but I like who are you and how did you get into this?
Awesome. So my name is Daniel. I go to college here in Boston. I'm originally from Ethiopia, and I got into this sort of with
Ethiopia, not Eritrea, huh?
no, not Eritrea. The
Do you
better
read?
half.
Do you read and speak?
I read a little bit. I'm not as proficient as I used to be, but I do speak pretty well.
Cool.
Yeah. I spent some time in Kenya. So my younger days were in Kenya from like age 2 to about 12. So I grew up there, spent about 3 years on and off in Germany, and then back to Ethiopia. And now I've been here for the last 4 years.
Wow, your English is impeccable. You
Yeah,
speak you speak German too?
no, I don't. I don't.
Oh,
German's a hard one. German's a very hard language. No, my mom worked for the UN, so we were sort of forced to travel quite a bit. Grew up
interesting.
a lot of international people in my life. Yeah. So
Cool.
yeah, and then
And how did you get into this and what are you doing?
so I consume podcasts a lot. I love podcasts.
Do you listen to Brett Weinstein?
I do listen to Brett Weinstein. He's Eric
I'm
Weinstein's
about
brother.
what?
He's Eric Weinstein's brother, right?
Correct, yeah. I'm about to be my podcast with him, or his podcast with me is about to be, I don't know how you put it. I was on his podcast and it's being released today or tomorrow.
I know. I was going through your Twitter feed and I saw that. I'm definitely gonna watch that when
What
it
you
comes.
did? It wasn't
Yeah,
on my
I,
really?
yeah. I think you posted that on your Twitter. You said something about Brett Weinstein. I was just looking at it right now, actually.
All right, well, all right. I don't think I said I mean, I'm waiting to see that it actually gets released before I'm not gonna count my chickens before they're hatched. But anyway, just we'll see. So that's what his staff told me.
Oh, okay. He has a staff. See, me and him are
Oh,
very
his son, his engineer and manager.
his engineering manager.
That's
Did it go well?
what?
Did it go well?
I'd give it a B plus.
A B plus.
If I could have done it again, I would have done things slightly differently. So maybe someday I'll get round two with him. We'll see.
Oh, I'm
Yeah,
sure.
there were some things I forgot to mention that I really wanted to mention, and there were some things we went down some rabbit holes on that were like probably slightly boring, but overall it's okay.
Yeah,
I mean,
it's sort
I love the guy. I love the guy. I think he's a hero and a saint. But I'm a little bit outside the normal distribution of his guests. He doesn't usually interview aerospace engineers, physicists, and stuff.
you certainly are. I mean, he has a very interesting story as well. I think
Oh,
his evergreen story and whatnot are quite interesting.
yeah. Do you mind if I'm vaping during this, or should I cut it out?
Not at all. Not at
Okay.
all. Not at all.
It's not just nicotine, by the way, for everyone who wants to know.
Yeah, no, that's an Alpha bar, right?
Yeah,
Yeah.
right.
I don't vape myself, but I have a couple buddies that enjoy.
Yeah.
Enjoy. And I was going to tell you to grab a cup of wine if you wanted, but that's okay if vaping is your thing. But it's okay.
Yeah, I'll wait on that. Depends how long this goes. It's a little early for me to start drinking.
It's true. What time is it there? It's still 2 p.m.
It's 2 p.m.
2:15. Okay. Awesome. All right. So I think it'd be pretty. So I want to understand a little bit more about your background and sort of your upbringing, because there's nothing about where you grew up. Did you grow up in St. Louis?
No, so let me just give you the 2-minute autobiography. I was born and raised in Chicago.
Okay.
I was born and raised on the south side of Chicago, which while I lived there as a child, went from being sort of a working class neighborhood to an pretty much all African American neighborhood with like white flight to the suburbs. And we were like pretty much the last white family in our neighborhood. And my school, I was in the public schools, they got really violent. And so my parents put me into a private school, but we remained living in that neighborhood. They put me into a very, very interesting school called the University of Chicago Laboratory School, which was a K through 12 school that the University of Chicago runs on campus. And they use it as a laboratory for their Department of Education. So they train graduate students in education, i.e. teachers, at this school that they run. And it's a school for, quote, gifted children. And so I got in and I got to go to elementary school at the University of Chicago, which was a truly amazing thing because we got to have like our science classes in the old science labs of the university because all the scientists had moved to the new labs. So we were in these labs with like all these old oak cabinets with taxidermied animals and like electrostatic machinery and stuff. And then we got to have our music classes in the, we'd be waiting out there in the music building of the university, and the university orchestra would be rehearsing, and then they'd come out and file out of the rehearsal hall, and us little 9-year-olds would file in and start, doing band practice. And so it was really amazing because we got to see university life. I got exposed to the computer lab. Like this was in the late 60s, early 70s, when a computer lab took up a whole building and with one computer. And so, yeah, I got to like have this exposure to this advanced intellectual stuff when I was a kid, along with everyone else who was in this interesting school. And then my parents finally fled to the suburbs of Chicago, and we moved to a fairly affluent place. And I went to an affluent, rather famous public high school called New Trier, and went to a program inside that high school that was an alternative program that allowed you to make your own classes. And so, I got to study calculus and architecture and all these things when I was in high school, just because I wanted to. And then eventually I went to college at Washington University in St. Louis to engineering school, majoring in computer science and math, because back then computer science was like the hot field. And because of my weird upbringing, I sort of had a bit of an edge, and I got to, I got in. Like I also applied to, I think, Caltech and stuff like this, but I was kind of selfish about this, and I like wanted to be one of the smart guys at school rather than be like, if I'd gone to Caltech, I would have probably been in the bottom, quarter of the intelligence level of the people there. But here I got to be sort of, reasonably elite. I mean, WashU was a great school, but nevertheless, it was a good match for me, and I had really good professors. And I learned one thing, which I want to tell any of your younger listeners, is that kind of the most important thing if you go to college is to figure out who the best professors are and take their classes. It doesn't even matter what they're teaching. They could be teaching art history, they could be teaching music, they could be teaching literature, or they could be teaching science and math. It doesn't matter what they're teaching. All that matters is that they're excellent teachers, because then if you take their class, you will become inspired to learn, and you will change and enrich your life by having the mentorship of these great professors. So who you take from is much more important than what you take. Just a little point. And I discovered this by accident on my own, and took from really amazing professors. And then I was staying there for grad school in computer science, and I'd already started.
Sorry to stop you. I was just wondering if were you into music at any point? Were you, because you mentioned.
Yeah. I like played in a rock and roll band in high school, and also took classical music lessons. I was never super talented, but I was very interested in it. And because of my math and physics interests, I was very interested in music theory. So, it all kind of blended together in my head. And then but when I got to college, I didn't do much music other than take a few like music history classes.
What instruments did you play?
Keyboards, percussion for a little while, and then keyboards, and piano and harpsichord mostly. And then but I kind of stopped practicing and playing when I got to college, mostly, not entirely. And then started to study jazz a little bit, but jazz is hard. And so yeah. So anyway, but yeah, I've always been interested in music, and I've always been an avid listener, and still am. And in fact, I was just reviewing YouTube videos of Gustav Holst's Planets suite to share with some friends.
What does he do? What's his
Gustav Holst is a long dead classical composer, considered one of the great orchestrators of our time. And he wrote a very famous orchestral suite called The Planets, which you must become familiar with. because it's one of the great pieces of orchestration ever made, and it's a really interesting work of classical music. Anyway, so yeah, so went to college. I was taking some graduate classes, getting ready to matriculate into a master's program in computer science at WashU. And then these companies started, they were coming, like this was a typical engineering school where companies send their headhunters to the engineering school to interview people who are going to graduate to see if they can entice them to, or find a good match and get the people who are good matches to come work at their company. And NASA was coming to interview at my school. And so I had always wanted to work for NASA, but I grew up in a time when NASA was kind of on a decline post Apollo and all this kind of stuff. And so when I heard that NASA was interviewing at my school, I was like, well, geez, I should at least go check them out. So I went for this job interview with these NASA headhunters who had come from NASA Ames Research Center in Silicon Valley, which is not one of the biggest NASA research centers, but a very interesting one. About 3,500 people worked there when they came to interview me. And it turned out one of the projects they were interviewing for was a project that I had just done a big paper on in one of my computer architecture classes. And because NASA.
Do you happen to remember what the paper was about by any chance?
Paper was entitled Array Processor Architectures for Computational Fluid Dynamics. And it was a survey of specialized computer architectures for solving, for doing digital simulation of aerodynamic flow. And one of the projects that was sending out these people to interview for them at NASA Ames Research Center was this project that was trying to make a digital wind tunnel, like a thing that would simulate what a wind tunnel does. And I had just done an undergraduate thesis, if you will, on these kinds of computer architectures featuring this one project from NASA. And so I knew more about this project than the people who were coming to interview me. So they were like, okay, you're a perfect match. We're going to fly you to California to interview with the actual team. So I flew out to California. It was my first time ever to the San Francisco area. And, it was my first time ever renting a car. I was this, young undergraduate. And so I'd never seen the Bay Area. I drove up to San Francisco and floated around, and I was blown away. And then, having grown up in the Midwest, it was quite a change. And then I interviewed with these guys all day, spent the time, and they loved me because I knew all about their stuff. And so, I loved them because they were like just these names that I had seen on papers. And now here I am talking to them in their lab. So eventually they made me an offer and I accepted, and I dropped out of grad school and I went to, picked up and moved to San Francisco. And that's where I met Jack, by the way, very quickly, like within weeks of maybe even less of living in San Francisco. I just ran into him in the Cafe Trieste and we started bonding over math and stuff like that. Because he was reading some math book at this table in the cafe, and worked with him on and off ever since. And then, I worked at a whole bunch of different things at NASA, which you can ask me about if you want.
Yes. So
let me basically go through my sequence at NASA, and we can then focus in on whatever you want.
sure.
I got there, I was involved in writing just computer system software, like operating system enhancements, device drivers, kind of low-level stuff, networking stuff. This was like the very earliest days of what became the internet. So I was writing device drivers to put our big computers on the internet, because back then the internet was only a place that certain small computers were on. NASA Ames was one of like the first 10 nodes on the internet back when there were 10 places on the internet. And it wasn't even called the internet then, it was called the ARPANET. And but it was the same protocols, the same software that we're still running today, basically. And which is crazy. It's crazy that software that was developed to run a computer network of a few hundred nodes can now run 100 billion nodes, but it happens that the people who designed it were really prescient and really intelligent. So anyway, be that as it may, I worked on that low-level system software stuff. Then I started working on, I got to associate with these scientists who were actually doing the aerodynamics simulations using these computers. So I started learning that stuff and started working on aerodynamics simulations on early parallel computers. And then, we used to call them massively parallel computers because they had the few thousand CPUs. Now that's not a huge deal anymore. And then, now a single GPU is way more powerful than these big multi-million-dollar computers that we were messing with. And then I got to work. Then got it really, because of Jack, I kind of got back into quantum mechanics, and I got really into quantum molecular physics and started working on molecular physics and chemistry, computational chemistry, as it's called, particularly ab initio quantum chemistry, also running on big computers and using also the new generation of graphics workstations to make visualizations of molecular phenomena. And then from there, I got kind of, okay, that led me into nanotechnology. So then me and a couple people at NASA started up what was actually the first federally funded research lab for nanotechnology. It was at NASA Ames. We called it the Computational Molecular Nanotechnology Group. And we did a fair bit of work and ended up winning a very important prize called the Richard P. Feynman Prize, which is given every year in nanotechnology. And it was just like 6 of us who won it together from NASA that year. I was just one of them. And then I got to work, and then I started working on big data visualization stuff. That's a whole other branch. And then I started working on optics and optical system design for what's called millimeter waves, and then eventually for visual optics, space propulsion. And then a whole interesting set of changes happened at NASA that were of a good advantageousness to me. And so I started working on space mission design. And then once I had done a few rounds of that kind of mission design stuff, a bunch of friends who had recently come to NASA, younger friends, by this time I was in my late 40s, a bunch of friends had arrived at NASA along with some new management. And they weren't my friends when they arrived, but I made them my friends. And then they went, and we were all living in this community house in Cupertino. This is all documented in this new book by Ashley Vance called When the Heavens Went on Sale. But we all were working together at NASA, and living together at this house. And then they decided to start building nanosatellites in the garage at the house. And they eventually resigned from NASA and formed a company, Planet Labs, eventually became known as Planet Labs, to build and launch and operate imaging satellites and then sell the data. And so about 2 years or 2.5 years after they formed that company, I quit NASA and joined the company, where I work to this day as like chief scientist and director of R&D. So there you have it. We can end now. That was my whole story.
So that's quite the journey, quite an illustrious story. And you spent 32 years at NASA, right?
Correct.
And so at what point in that journey did you go to Stanford?
Oh, well, NASA, to their credit, had a very nice relationship with Stanford, at least NASA Ames did, where like if you could get accepted into Stanford, NASA would allow you to attend a certain number of hours per semester and still pay you a full-time salary. I mean, you couldn't be a full-time student, but you could be a part-time student at Stanford, and they would pay your tuition and pay your salary. And so I did that for a while, but unfortunately, I had a great advisor, but I didn't have great professors. And I just was like, ugh, this isn't fun. My job at NASA is so much more fun than being a graduate student. I'm just going to do my job. And it's like, because I was like, well, let me think about this. If I get and graduate, from Stanford with my degree, and if I'm really lucky, I'll get a job as good as the one I already have. So I'm just going to stick with what I got. So, this is a dubious, in retrospect, I might have been better off pushing through and getting the degree, but I've done okay.
You've certainly done okay. And
but
so
you can't call me Dr. Levit because I dropped out.
okay. So interesting. And then you said you mentioned that you started the supercomputing division at NASA Ames.
Well, yes, I was one of the co-founders of it. I would say I was hired in as a junior person right when they were starting it up, but then I ended up being one of the people who'd been there the longest. Like after about 10 or 12 years, there was one brief time where I was both the youngest person on this project and the person who'd been there the longest, this supercomputing division project. But you know, I was never very political back then, so lots of people climbed the management hierarchy, and I just did R&D that was interesting to me. And so, you know, I was never like in charge of it, although I like to think that I was, you know, behind the scenes, kind of pulling some strings.
You just to poke at what you just said right now, you were never so political back then. Were you more political now?
Well, in the case I just mentioned, what I mean by political is like office politics. Like I
Yeah,
was
I know.
like angling for management positions and, you know, lots of direct reports and all this kind of stuff. That didn't appeal to me. I wanted to do technical research in the field, in the areas that were inspiring to me. And so I did not, you know, rise through the management hierarchy. Occasionally I would have a small team that I was responsible for managing. And occasionally we'd switch out the roles and someone else would manage the team, because we were basically collaborative. But we were always like a small R&D team embedded inside a larger kind of operational team. Yeah, but so by political, I mean office politics. I mean, these days, you know, everything is political. So yes,
Yeah.
I am more political these days, although I do have to somewhat uh
Aim yourself.
uh, yeah, there's multiple reasons to aim myself. One is because you have to choose your battles, you know, and the other is because, you know, I am part of a larger organization now, so I can't just like go off like completely spewing, you know, whatever rant that I'm currently enthralled with, because I don't want to reflect poorly on my colleagues. And so it's a difficult thing because, you know, one wants to be authentic and not self-censor, but one also wants to be considerate and judicious and choose your battles.
Yeah, it's somewhat of a constant dialectic.
Yeah.
So so what is supercomputing? Because I'm sure. So is that just like parallelization of a bunch of extremely powerful GPUs? What's
Well, back then there were really no GPUs, or there was just the very earliest glimmers of GPUs from companies like Silicon Graphics and stuff like this. Um, Parallel computing is what it amounted to. In our case, then and even now, we kind of specialized in a particular kind of parallel computing, which is basically shared memory parallel computing, where you have multiple CPUs, but they, in some sense, have access to the same global memory. It's not all at the same speed, like they actually have local memory that's faster and global memory that's slower. But nonetheless, to solve really big problems in computational physics, at any rate, you kind of need to have like a global memory abstraction, if not a global memory fabric and architecture, so that uh, you can solve problems that extend over a large region of space where you've gridded it up to a very fine level of resolution. This is somewhat different from classic, like embarrassingly parallel problems where just each little CPU is working on its own thing and doesn't have to communicate with anyone else. So, you know, nowadays, like with data centers, this is getting a bit blurred. There are these, you know, big shared databases, and what do they used to call it? It's kind of obsolete now, I think. Not map, that's another thing, but there are all kinds of abstractions to make it seem like you have a large global memory when you really have a bunch of separate CPUs with separate memories. And, you know, this gets into sort of classic problems of computer science, cache coherency and thread safe, you know, race conditions, all this kind of stuff. And now there's all kinds of algorithms that are not so sensitive to that, not so much for databases, but for like certain kinds of statistical computing. You can sort of sometimes ignore collisions and race conditions because it's all approximate. But for the computational physics, by and large, computational aerodynamics, quantum chemistry, climate modeling, astrophysics, these sorts of things, you do have to enforce consistency on when the memory updates. So I haven't been into that stuff for many years. I'm kind of
Yeah. So
on.
were you guys using the supercomputers mainly for sort of trajectories or
Oh, no,
what?
no. Trajectories are actually really, really simple compared to the stuff we were doing. No, we were using them for mostly fluid dynamics. So that would be aerodynamics, numerical weather and climate, astrophysics like plasma physics and stars and stuff, cosmology, large scale structure of the universe, and also quantum chemistry, and maybe some other things too. But
Interesting.
basic computational physics, not so trajectories. Technically speaking, is what's called ordinary differential equations. Like you're just looking at one trajectory. That's something you just kind of sequentially figure out where it goes. It's something you can do now on a very small computer, actually. Now, you might want to analyze thousands of them in parallel, but even that is not a very big job. But when you're working with things like fluid flows or quantum molecular systems or cosmology or astrophysics, you're not solving what are called ordinary differential equations. You're solving what are called partial differential equations, and they involve much more work and much more calculations. And fortunately, much of that can be done in parallel, but not all of it.
Right. And so quantum chemistry, quantum, just this buzzword that somewhat loses people at times.
Yeah, let me explain what I mean simply.
Okay.
If you're doing molecular physics, modeling molecules, you can choose various levels of fidelity. If you're going to model big molecules like proteins and DNA and this kind of big solid state systems, like if you're going to model things that contain hundreds or thousands or even hundreds of thousands of atoms, you kind of tend to model them as just like balls on springs. So it's more like Tinker Toys that are kind of a little bit elastic, and the different types of atoms and the different types of bonds have different. It's a very classical system. It's like literally balls on springs. But that doesn't help you to understand things like chemical reactions, like bonds forming and breaking very much. If you're going to go to that level, you can't do as many atoms. You can maybe only do a few or a few dozen. And you have to model the fields, essentially. And that's where it becomes quantum chemistry, really, where you're modeling technically you're modeling the quantum wave function, but you can think of it as kind of just like fields that fill space, electron clouds and stuff like this. And that is much more computationally intensive, which is why you can only do small molecules. But it's much more accurate, and you can predict things like chemical reactions, bonds forming and breaking, new molecules forming, and other detailed properties. And that's what I was more involved in.
And was that useful when you sort of moved into the field of nanotech, or when
Well, most nanotech uses the balls on springs kind of stuff, but nowadays the field has gotten so big that people do all sorts of different things in nanotech, and some of them do this kind of quantum chemistry, and some don't. But I was mostly focused on quantum chemistry for my part of the nanotech effort.
and okay, so the applications for sort of the quantum molecular simulations that you were building was for nanotech.
Eventually, yes, mostly that. It started off with more general, with a broader set of problems, but eventually, yeah, that's what I focused on.
Interesting. And are there any other applications that you think, well, I mean, I can imagine that in some sense it's sort of just like the idea that we can engineer things at different scales, and the ability to engineer things at smaller scales would obviously grant us more applications at larger scales. I assume. Do you think that
Yeah,
there?
well, nanotechnology has gotten to be a pretty big field, and like it's also one of these buzzwords that's become sort of a funding hotspot. So what people used to maybe call, molecular biology or material science or just plain old chemistry, they call it nanotechnology now because like that gets the funding agencies excited. So all different techniques are used now in the nanotechnology field, the balls on springs or molecular dynamics techniques, as well as the quantum techniques, as well as other techniques.
Interesting. Yeah, I've always thought of nanotech as just being somewhat somewhat of an eventual destination would reach as technology progresses over time, because we'd want to engineer things at smaller and smaller scales over time anyways.
Yeah, yeah, you're absolutely right about that, and that's been a consistent theme of the field of molecular nanotechnology since its inception in the early 90s. But I want to say something that people need to remain cognizant of if they're interested in this is, to some extent, nanotechnology is still a very speculative kind of end goal where we aren't there yet. Like, we don't really have, if you will, real nanotechnology applications, one might argue, unless you're looking at, we actually have an example of absolutely exquisite nanotechnology that works, and that is biology. Like, biology is molecular machines that do all sorts of, everything our cells do and our bodies do and every organism does is molecular machines, molecules, very big molecules, in many cases, making other molecules. And that is molecular nanotechnology. So, and this is something that the field has always sort of recognized, that we've always had this example of working molecular nanotechnology, which is biology. And that makes us think it's possible, Now, the goals of where sometimes referred to as machine phase nanotechnology is different than biological nanotechnology. Biological nanotechnology is wet and it relies on water, and the molecules tend to be kind of softer, although that's an illusion. Actually, they're not soft at all at the nanoscale. They're just, we think of like our skin is soft, but it's like at the nanoscale, it's like extremely rigid. Like, we think of cells as like this bag of gelatinous stuff with spaghetti and other gelatinous bags inside them. And it's like, it's not that at all. So here's a good example of what I mean. If you take a wine bottle and let's say we fill it up with water and we turn it upside down, the water will all flow out in a matter of seconds. Now, if you shrink that bottle down by a factor of 10 and turn it upside down, you're going to have to shake it really hard to get the water to come out. And if you shrink it down by a factor of 1,000, that water just will not come out no matter how hard you shake it. And that's because as you shrink it down by, say, a factor of 10, the mass decreases by a factor of 1,000. So the mass of the water is 10 cubed. Mass of the water is the volume of the water, and hence the mass of the water is 1,000 times less. But the surface tension does not decrease by a factor of 1,000. It only decreases by a factor of 100 because it's an area thing. So if you decrease the wine bottle by, say, 1,000-fold, now the mass has decreased 1 billion-fold, but the surface tension has only decreased 1,000-fold. So now the ratio of the surface tension forces to the inertial mass forces are 1 million times higher. That's why you can't shake the water out of a microscopic water bottle. It's because the surface tension, relatively speaking, is 1 million times stronger compared to the gravity than it was at full scale. And this is what's going on in our cells. The surface tension forces and the forces between the molecules are millions of times stronger compared to the mass of the stuff than we're used to at our scale. If we fill up a bag of water at our scale, we're used to it just being a complete floppy mess, right? At the scale of a human cell, if you think of the cell, which is mostly water, with all the various filaments and things inside of it, it is not like spaghetti. It's not like cooked spaghetti inside of jelly. It is more like steel rods inside of stiff clay. Like, that's more like what it would be if you were down at that scale. That's what it's like. It really is like almost rigid machines. And so that's an important thing to know about even biological nanotechnology, is that it really is much more machine-like than we would think if we're looking at wet biomaterials at our scale.
think that that's a wonderful point to make. Would you consider transistors nanotech?
Well, I mean, I might consider VLSI approaching nanotech. Like when you've got feature sizes on modern chips that are, uh, you know, 10, 20 nanometers in size. I mean, I know they claim that the features are smaller, but I mean the actual transistors. Is that actual nanotechnology? Well, technically, most people in the field would say no, because you're not engineering, you're not building the molecules up. What you're doing is you're taking bulk material like silicon and you're etching it, which is kind of like using steam shovels and, you know, back. It's kind of like you're moving bulk material around. Like at the level of atoms, these things are still fairly big, but we're approaching it. And there are people making, and I worked somewhat on this a little bit, molecular transistors. They're not in production yet for any purposes, but they are possible. It's possible to make electronics at the molecular scale, diodes, transistors, things like this, but no devices in, no human-made technological devices actually utilize these things for any commercial purposes at this point. They're just laboratory curiosities.
What are the sort of set of tools that you'd use to make object molecular sized transistors?
Well, there here in this is the problem. We don't, you see, to make it's sort of a chicken and egg problem, which is that to make machines at the molecular level by putting atoms together one by one,
Mm.
you kind of need machines at the molecular level that can do this. And so you have this problem. It's always been turned. That was the problem of the assembler. Like we want to make a molecular assembler, but the problem is you have to have a molecular assembler to make a molecular assembler. So, or at least it seems that way at first. So it's kind of a conundrum. And so there's a gap between theory and practice. And in a sense, that gap is waiting for progress in this generalized molecular assembly. Now, biology solved this with essentially with the ribosome, among other things, which is a semi-general assembler that can make different proteins based on genetic codes. And the proteins can serve millions of different purposes. It's not a fully general molecular assembler by any stretch. It can only make proteins, but nonetheless, proteins are a very versatile class. They can be structure, they can be machines themselves, they can be catalysts, they can be yeah, they can be so many things, but it's more complicated than that, of course, because there's other molecules besides proteins that are involved in biology, like lipids.
Yeah, I think
Very, very complicated.
yeah, one of the things that I find very interesting about nanotech, especially in relationship to sort of biological systems, is that I feel as if, I mean, I'm sure you know this, but there's been huge interest as of late in biotech as a result of sort of COVID and competence in government as a result of that. And so
Ooh,
there's sort of this
getting
need,
into dangerous waters here. Let's go.
yeah, dangerous waters, incompetence in certain branches of government.
Oh, pretty much all. But anyway, go ahead.
Pretty much all. You're much nicer than I am.
Uh-huh.
And so, the reason why I ask what set of tools one might need to build these molecular machines is because it's sort of hard sometimes when, doing work at the frontiers to understand where to start.
Well, I think if you're gonna make biological things, be they therapeutics or repair wounded systems or new organisms, even synthetic biology. I mean, that's all based on biology pretty much. I mean, you can put in certain tweaks like, for better or for worse with the mRNA vaccines, they used pseudouridine and like, so they're making alterations to normal biology. And that's not the only case by any stretch, but for making biological nanotechnology interventions, you kind of start with biology. Even if it's synthetic biology, you're kind of starting with biology. And but to make, like, if you want to make nano electronic circuits or nano materials for building and construction or industrial processes that are non-biological, now you don't start with biology in general. It's a complicated field. I mean, in a way, it's kind of silly in a way, because anything made of atoms, which means anything in the universe, we can call it nanotechnology because it's made of atoms, you know. It's like, it's kind of a bit of a overly broad catchphrase.
Yeah. No, very true. Very true. So you spent a lot of time working on simulations, I take it.
Yeah, I haven't spent much time in the lab. Um, uh,
And and despite having gotten a degree in aerospace a little bit, do you have any sort of recollection from your?
well, my actual degrees were in computer science and applied math. I
Yeah.
dropped out of the aerospace engineering graduate program. Um, and had I stayed, I probably would have done simulations there too.
Yeah.
So yeah, I mean, I did a lot of work in labs. I took a sabbatical from NASA for a few years to run a privately funded research lab,
Hmm.
um, that was looking into sort of exotic space technologies, exotic propulsion, exotic energy stuff, kind of fringy stuff, but really fun. And we had a lab, and I had a few techs working for me. And so I got into a certain degree of, like, you know, electronics and machining and the kinds of things you actually do to you actually need to do to build benchtop test equipment. We even did some plasma physics stuff. And uh,
What were you guys trying to build?
we were trying to look for any sort of space propulsion system that had the potential to really change the game in space propulsion. Sometimes they go by the name propellantless propulsion or exotic propulsion, as well as some related things in energy production. Uh, we sort of divided our time and money into three broad avenues. One was our own experiments, which were basically done by mining the kind of heretical science literature, trying to replicate things that showed anomalous results from previous researchers who'd been sort of overlooked. The second avenue was funding outside organizations who made proposals to us to do similar work, compact fusion reactors, that sort of thing. And then the third thing we did was we went to visit other labs or had them come bring their stuff to us if they thought they had some kind of special experimental results which were exceptional. So we had a test lab where we could test various energy production and propulsion claims, as well as kind of go on field trips to remote locations and look at things that others had developed. Even we went to Russia and Hungary and all over the US looking at like kind of crazy garage inventors and things like this. It was super exciting. Something that I am gearing up to do again, but this time at a more professional and sustainable level.
That sounds like a lot of fun. Was NASA funding this? This doesn't sound like something.
No. NASA actually threatened to fire me after a while because they were like, you either have to come back to work or we're going to replace you. And so that sort of coincided with the bursting of the first internet bubble. So our funding kind of dried up. So I went back to NASA. But I've always maintained an interest in these sort of heretical, exotic applied physics uh, speculations and claims. And so it's one of these things where my experience as well as my intuition tells me that most people who make these claims that they've invented an anti-gravity machine in their garage or whatever it is, like most of them are either deluding themselves or trying to delude investors or both. But you know, it's still important because if any of them are right, it's really important. So I kind of feel like, well, you know, why aren't we spending like 1% of our science budget on exotic, kind of unbelievable claims? Because it's surely worth a small amount of investment. It's like kind of, you want a balanced portfolio, you know, you don't want to spend all your money as a society or as a government agency on like crazy stuff, but you probably want to spend a tiny bit of your money on crazy stuff.
Yeah, I think that's a very good point. It's funny to me because I always find that people who work on so-called heretical sort of physics science slash
Mhm.
science speculation either tend to be extremely curious and open-minded people, or they tend to be extremely conspiratorial people, or they tend to be very low integrity people. So it's always
Yeah,
one.
yeah, and I think you've got something there, but not all of them. I mean, some people, yes, there's a lot of conspiratorial minded people and a lot of low integrity people. And what was the other kind?
Just open-minded and extremely curious.
Well, yes, and yeah, well, there's a lot of different types, and after a while, I kind of tended to be able to recognize who I was dealing with pretty quickly. But even though I'm very skeptical, I'm also want to give everyone a fair shot. So even if, and I met a lot of these people, even if they were quote unquote crazy, I'm still like, well, you might have discovered something, even if you're crazy. So let's have a look. So that's kind of where I'm coming from on this stuff.
Yeah,
In
that's
fact, I learned from one of my mentors to actually be highly amused by the crazy ones. Like he was like, "Oh, this is going to be fun, Creon."
a good way of looking at it. Yeah. It's always best to be open-minded at the beginning and then critical afterwards. So so did you guys discover anything? Was there anything that came out of it? Anything?
Yes, there were some interesting things that came out of it, but unfortunately, we had to put them on the shelf when we ran out of money. Now, I will say that a few of these interesting things were eventually taken up by other groups and have become like full-on companies with a large amount of funding. In particular, one of the compact fusion reactor concepts that we were funding in my organization eventually sort of became the company that is now called Helion. Um, and I mean, not directly, but but the but the but the but the lineage is like straight through from the experience we were funding to Helion. I don't even know that the Helion people know this. I mean, they know it, but they don't know the role that my organization played. But it would be great to get together with them and
I,
discuss it.
yeah, Creon, I think it'd be great if you mentioned because you know, for someone who might not know what Helion is, Helion's probably the furthest ahead in terms of sort of fusion reactor designs. No,
This is
right?
hard to know because a lot
Yeah.
of this being privately funded is not regularly published and reviewed and stuff like this. But Helion is certainly one of the most well funded of the compact fusion reactor, privately funded compact fusion reactor efforts. There are a few others. I try to keep track of them, but quite frankly, this field has gotten really hot, like with Sam Altman and other people like getting involved. It's like, okay, I'm not going to try and compete with multi-billionaires on their pet heretical science, even if you want to call it heretical. There's pet like sort of disruptive science projects like it. Compact hot fusion has kind of graduated from crazy little labs to like a bunch of competing startups. Uh, uh, Helion is certainly one of the ones. That Tri Alpha is another one. Lawrenceville, General Fusion,
And TerraPower,
TerraPower is fission, and
the fi-
TerraPower recently changed what they're doing, from what I understand, or somewhat recently.
okay.
I mean, fission is another thing. Like fission is like that's fission power, and there's many advanced fission power reactor companies, but like that's like very capital intensive, more so even than fusion in the sense that you get into this whole regulatory regime and construction, all this kind of stuff. Like fusion is still trying to even show that it works. Fission is like trying to build an economical reactor that's competing with a bunch of existing ones. So that's a whole different story. I mean, I think it's wonderful, but it's not something that I would get involved in because it's oversubscribed. Even cold fusion, which is sort of on the outs right now, but there's still people working on it. Low energy nuclear reactions, even that is oversubscribed from my perspective. Like I would not dive into low energy nuclear reactions if I was running this organization, which I will be when I'm running a similar organization in the future. Like I'm going to be looking at stuff that's undersubscribed. That's where I want to go. I kind of am not interested in pursuing things that a whole bunch of other people are already pursuing. I'm like, you're already doing it. Like, what am I going to add?
And it's very wise advice. Yeah, so
Yeah, it's sort of the Peter Thiel philosophy of 0 to 1. You know, that's where I'm interested in prospecting.
yeah, mimesis, I think. So yeah, so I think it's anything else outside of sort of compact nuclear reactors, because sort of, Jack has his ideas, but is there anything else that that
Well, I'm interested in Jack's work and always have been, and have done a little bit of it with him. Jack is more of a theoretician.
yeah,
He's partnered here and there with experimentalists. I haven't been involved actively in any collaboration. Jack was actually a theorist that I had on staff at this organization 22 years ago when I ran it, but because we did some theoretical work as well. But I'm very interested in Jack's work in the sense of if we can do any experiments that actually test it. I'm interested in his theoretical work also, but that's mostly just at an intellectual level. But in terms of potentially funding his work, it would require some kind of experimental plan for experimental verification, which could very well be within reach, but I haven't looked at it very closely in recent years.
yeah. So he speaks a little bit about, I think, something that to many people seems at least logically coherent, which is sort of this idea that you have metamaterials that are pumped with these Froelich condensates, and those Froelich condensates cause this lift property when pulsed in the current.
Yeah. Okay. Look, I don't want to get into a detailed analysis of Jack's theories. For many years, perhaps even longer, he was into this Froelich stuff. But I think more recently he might be have realized that is it's sufficient, but it may not be necessary. Maybe we'll do this other ways as well. And whatever the case may be, this is the kind of thing which, if it's true, it should be possible in a lab to like just nail it. I mean, not to build a flying saucer, but to like show that something's going on. But to say to people that it makes sense to people, I'm a little bit skeptical of that. Like, I know a fair amount of physics, and I've known Jack for decades, and I can only follow his stuff up to a certain point. I'm not trying to say that he's wrong. I'm trying to just say that a lot of it is outside my reach. And you can say metamaterials and you can say Froelich condensate. That doesn't mean anything's going to work. And by you, I don't mean him. Like, he may have a coherent vision, but for people to say it makes sense to them, it's like, okay, really? How many papers have you written on Froelich condensate? And why are metamaterials even relevant at all? It's like, these are words. And for most people, they're just words. So, I'm not trying to knock his stuff. I think his stuff is some of the coolest, but nonetheless, it's like, look, my basic position on all this stuff is theory is very nice. Show me something in the lab. And if it seems to work in the lab, we can talk about the theory. But if you don't have any idea for even how to get anything to work in the lab, then I'm not all that interested in discussing the theory, because it's just an intellectual exercise, and I'm more interested in something of pragmatic value.
Yeah, I think, yeah, I'm very much in alignment with that. I think one of the things, and you brought this up, is that there's such a large body of work nowadays, in every field, and then there's subfields to fields. And I think this is somewhat where AI can help a lot in sort of aggregating that knowledge and summarizing it for people. Do you feel as if that there's just too much information now? Too many papers?
Well, I have to unpack what you said, because I'm a little bit possibly in disagreement with the thing you said.
Sure.
But here's what I mean with that. Yes, there's a lot of work. I mean, there's more scientists than ever. There's a lot of fields and there's a lot of subfields, but there's also the kind of other problem, which is that there is a real somewhat of a kind of groupthink going on in science, and people are reluctant for various reasons to do the kind of things that Jack is doing, which is going out on a limb. He's not part of the academic establishment anymore, so he can sort of do that. As kind of few others who we know about, but inside of the academy and inside of government and inside of industry, people are much more often than not discouraged from saying anything that's too crazy. And so, yes, there's a lot of work, a lot being published, but I'm not quite sure how much of it is like really disruptive. Some of it probably is. Then the other thing is, getting onto your AI comment,
Yeah, so I probably didn't say it in the right way. What I meant was not that it's disruptive, but more so that because there's no one individual that understands all of these fields and the complexity that might be necessary. It's sometimes hard to aggregate that in such a way that you can move forward.
Yeah, I think that AI has shown some advantages possibly for doing summaries and stuff like that, but I have to say that, quite frankly, it mostly seems to fail when it gets down to deep knowledge. And what I mean by that is, if you don't know anything about something, asking an LLM is kind of the new version of asking Wikipedia. It's like, yeah, you can learn some of the basics, and it'll do a fair job of bringing in a bunch of relevant information and kind of making coherent summaries. But if you ask, what I have found, and this may change, what I have found is that when I ask these AI systems about stuff that I really know about, where I'm one of the people who knows like as much as anyone in the world about things, which is, not very many things, but a couple maybe, they don't do very well. Like, when you really know a field, they're not very helpful as far as I can tell at this point. In fact, they're quite confused. And in fact, I just read an interesting article about why they're confused. And one of the reasons they're confused, allegedly, is because they all train whether it's correct or incorrect. And in fact, when they get information that does not conform to their existing model, they upweight that information. This is this thing, I think it's called hard negative mining in classic machine learning, but it's like information that doesn't conform to your existing model. The idea is it should really update your model, because something's wrong with your model, because all of a sudden you're getting anomalous data that your model didn't predict. Well, the problem with that, in some cases in science, maybe the information is wrong, and that's why it doesn't correspond to your model. But if you update your model to incorporate it, now all of a sudden you give someone a summary and it's full of wrong information, because you kind of equally weighted everything. And I'm not, on the one hand, I'm not arguing for groupthink and like only giving the consensus opinion, but at the very least, it should be able to separate, like, here's the consensus opinion, here's these heretical opinions, this is the current situation. But instead, it kind of seems to mash all this stuff together. And it's a lot of times not even self-consistent. And so I am a little bit skeptical at the present time of the ability of AIs, of large language models, to make progress. I think they can help instruct students. But even then, I think that, as they say, you always have to check, you always have to question, you always have to know that they can hallucinate, right? Because quite frankly, these are still problems.
It's very true. I mean, I think one of the things that could help is, I mean, you mentioned that you would consider yourself somewhat one of the world experts in certain topics.
Very tiny little topics.
And I'd love to know what those topics are, so we could
heretical science, heretical applied physics.
Okay.
Maybe a little bit on molecular nanotechnology, although that's a field that's got a lot more people in it. um, you know, uh, uh, maybe a little bit on foundations of quantum mechanics, although that too has plenty of people who are more credentialed than I am working on it. Uh, yeah, and then some sort of weird hybrid fields that I'm trying to develop right now, like the intersection of remote sensing, AI, and regenerative agriculture. But that's a whole other discussion.
Interesting. Okay. So yeah, no, I was just gonna say that one of the things that would help is by, using people like you who understand these topics and are the best of the best, perhaps on the planet, at fine-tuning these models when it comes to that specific knowledge, right?
Yeah, I suppose. I'm also skeptical of fine tuning because,
Okay.
if I fine tune it, it's just going to have my biases. And if you fine tune it, it's going to have your biases. And it's like, I mean, maybe that's a nice way to um, widely distribute the expertise of an individual person is by putting it into a machine that then a million people can use all at once. But I'm a little bit, I tend to be one of these people who believes, I forget whose law it is, that like we always overestimate the short-term impacts of these technologies and underestimate the long-term impacts. And I think AI is at that stage right now. Everyone thinks AI is going to change everything, or large language models are going to change everything this year. And I'm not so sure about that. I think they may change a lot of things in 10 years, but I think they have a ways to go. And and there's a whole host of other problems as well, but we don't need to get into those. I mean, the whole I feel there's a dark side to the AI safety debate, and I'm by no means the only one who thinks this. Like, I think that like I'm not really interested in AI that gives me the government's opinion on stuff, unless I ask for the government's opinion. You know what I mean? Like, just go ask the AI. Hello?
Yep. I think we're back.
We had an outage. Yeah, I have a star. I'm coming to you by Starlink. So
Oh,
every hour or so, it drops off for
oh,
like
this is
30.
this is pretty good. I didn't know Starlink. I mean, it's been pretty good so far.
Yeah. Starlink is pretty good, except for like every once in a while, it just drops for 30 seconds because the constellation's not complete. Anyway, did you get what I said about COVID?
Nope.
I said, I said, I said, that I'm not really all that interested in safe AI. I'm not interested in AI that doesn't offend me or that makes sure to not give me any misinformation. I want uncensored AI, and I'll be the judge. Thank you very much. And I'll be the human reinforcer. Thank you very much. I'm not interested in being coddled or protected from, what the government or OpenAI or anyone else says is misinformation. I'm kind of interested in hearing it all and then making my own judgments. And as I said, like if you ask AIs these days, LLMs, about anything controversial, you kind of know what you're going to get. Like if you ask them anything controversial about COVID, you know what you're going to get. They're going to pretend like contrary opinions don't even exist because they've been especially trained on like politically sensitive topics. The old thing about like write a poem in favor of Donald Trump. It's like, sorry, I can't do that. It's like, oh, come on. Of course you can do that. It's like you might your creators might not want you to do that, but you can do that. Anyway, so it's like um anyway, I I understand some of the concerns about AI alignment and AI safety and AI risk, but I also think that like let's not throw the baby out with the bathwater and just make a bunch of um, um, you know robots that parrot the uh, preferred political narrative of the moment and refuse to speak of anything else. That doesn't sound very useful to me.
Very true. That's very true. I think the AI safety sort of conversation is a very serious one, especially now when we still have dumb AI. And we haven't gotten to the point where we have very intelligent systems that can act in the real world.
Yeah, but I mean, there's like we have a lot of quite frankly, they're talking about a pause. I'd rather see a pause on viral gain of function research frankly, than I would on AI right now. Like one has actually already killed millions of people, arguably. So like we might want to try and put that genie back into the bottle before we worry about the genie that hasn't escaped
but
yet. I know that that's a weak argument because some might say, well, better
Creon.
safe than sorry.
Oh yeah. Oh, but the idea that this escaped from a lab is most certainly a conspiracy, and that can't be true.
Well, a
Um,
racist conspiracy at that, yeah.
yeah.
I find it so ridiculous that they called it a racist conspiracy theory, and then it turns out that oops, it was the Americans that funded it. So yeah, that's a whole. I mean,
Yeah, Jack was telling me yesterday that he heard Vivek in sort of in sort of the speech that he was giving say that the time delay between conspiracies in real life now is about 3 weeks, which I
yeah, it's
found.
getting shorter and shorter. Yeah, right. It's getting shorter and shorter. Yeah. All the conspiracy theories that I was either told not to speak of or afraid to speak of on social media because didn't want to get banned, are now like one by one becoming speakable. And yeah,
They become
yeah,
more obvious,
those
unfortunately.
are interesting lists. It's interesting to list out the things that were conspiracy theories 3 years ago and are now like actual, you know, things that the Wall Street Journal will talk about. But
Yeah.
okay, we live and learn. You can look at this positive light too, which is that I mean, I'll tell you one thing. This is something I talked with Brett about, and he had his counter arguments. I must say, one thing I learned during COVID was that most people aren't actually interested in quote doing their own research or making their own decisions, and there's various reasons for that. They're too busy. They've got to put food on the table. They don't want to get in trouble. They don't want to lose their jobs or their privileges or their friends. These are all understandable things. But in general, I think there's another thing that's at work, which is that actually most people, and I think this is probably the case even before humans, like this is the case with chimpanzees, like most members of the tribe follow the leader. Like they have to. Otherwise, there's no such thing as a tribe. If every member of the tribe is doing their own thing, it's not a coherent group that can accomplish things as a group. They have to have a hierarchy and they have to follow the hierarchy. And so most individuals have been selected genetically to do that. But there's a few out on the tails who don't go along with the hierarchy, who do go explore on their own. That's like you and me. Okay. Now, you can't have everybody doing that, or there's no tribal coherence, there's no group action possible. But you also don't want to have nobody out exploring, because if nobody's out exploring, you never learn anything new. So I think what's happened is that we've evolved to have like 10% of the people are like anti-establishment, dissident, anti-authoritarians. And 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 during COVID, I was like really shocked and really disappointed. Like even my very smart social circle, like 90% of them just totally went along with everything without question. And at first I thought, you know, this is disappointing. They're not as smart as I thought they were. What the hell's wrong with them? And then I eventually realized that no, they're probably just genetically programmed to basically do what the authorities say in most circumstances. And, this is just unfortunately human nature. And so it may be something we have to accept. And this is, by the way, why much as I am hoping I'm wrong, I think that some of these anti-establishment political candidates, we don't even to put in their names right now, but I'm not talking about Trump here, but I'm like, say, let's talk about RFK and Vivek, to take one of each party. Like, I wish people would listen to them. I wish people would take them much more seriously. I wish they were much higher in the polls, but quite frankly, they're probably going to poll around like 10% or 15% or maybe max of 20, because most people are just like genetically repulsed by those who go against the hierarchy. And I'm not sure you can reason them out of that position, because I think it's wired in.
Yeah.
So I hope I'm wrong.
I do too. I do too. Um, I mean, we need it. Extremely volatile times now. Well, I think, just to get back to the AI safety conversation, because I think this is sort of tangential to that. It really matters who builds and controls these systems, um, when you're deciding who it is that, what their incentive is in allowing people to speak about certain things or allowing these models to learn about certain things.
Well, okay, let me say something about that. I think there's a chance, and this is of great concern to many in the AI safety world, and I realize now I should ask them about it, but I happen to have some friends who are founders of some of these big AI companies, just leave it at that. And there's, as well as some others who are kind of active in social media on this, even if they're not like, founders of multi-billion-dollar AI companies. Like, a lot of them will say what's actually going to happen is a democratization of AI, that you don't actually need giant data centers and, trillion parameter models to do high quality language models. I don't know if you've got GPT for all, but I've got it on my laptop. It's not the best unless you call out to GPT-4 or something like this, but the internal models that it can run are, reasonably good. And I'm pretty certain that if you have like a closet full of, if you have like a one rack of computers in your closet, you can probably run a state-of-the-art model. Now, you can't do what Microsoft is doing and run it for, 100 million people simultaneously, but you can run it for yourself, right? And so the fact that one might be able to run a state-of-the-art or approaching state-of-the-art LLM on a computer that's affordable by an individual, a normal middle-class person, that says to me that this whole thing might get democratized. And this is what one of my friends, who's one of the founders of these important companies, says to me. He says, AI is going to be like electricity. I mean, assuming we don't fuck up the electrical grids, it's going to be like a thing where you just get it. Like it comes out of the wall basically, and you get to do with it what you want. It's not like the electricity that comes out of the wall is, safety trained to only do certain things. That's like the electricity comes out of your wall. You can do anything that electricity can do with it. And so the same thing might be true with or the internet bandwidth that comes out of the wall. You can kind of, for now, at least with Starlink, you can use it for whatever you want. They're not going to stop you from, in principle they could, but it's like, if we're not inside a great firewall of America, then, the bits are bits, right? And amps are amps. And in a way, AI inferences are just like, it could be that it could be that there's at least a counterforce to centralized, censored, homogenized, boring, safe, quote unquote, AI. It could be that we have the ability to run our own, kind of like Linux, and so those who want to at least can depart from the guardrails and take their own risk.
I think that's somewhat a wonderful transition into this other conversation about distributed systems and perhaps the ways in which we can build AI on distributed systems. Do you have any ideas on the possibility of that? If that perhaps might not be feasible now because there aren't any distributed systems that have scaled.
Well, actually, I think there's somebody you might want to talk to about this if he's got the time, and that's Peter Wang, who's the CEO of Anaconda, and he's started up a new venture to make exactly this: a open source distributed large language model infrastructure where the content creators get paid for their content rather than the current systems which just rip it off, and where it is, that content creation micropayment thing would probably be, a blockchain thing, one would imagine. But his vision is much broader than that. It is a democratized system where not just the use and inference, but the training and training data are all distributed. I mean, not distributed in the sense that every time you ask a question, it's going out all over the internet, but in terms of the creation of these things is distributed. And so, yeah, I wish he's great person and a really brilliant person. And so I am very much in support of his work on this. I don't really see distributed systems for AI necessarily being used for just everyday inference, but I think in terms of the training, distributed systems could end up being a very important competitor. And I don't just mean economic competitor, I mean cultural competitor to centralized systems.
Yeah. And it's interesting because we started, I think, basically in 2009 when Bitcoin was created, was sort of the beginning of this building of distributed infrastructure around the world with things like Cardano, Ethereum, and other sort of competing blockchains. Do you think that there's value in that? Because it's so funny. I still meet a lot of people today, and a lot of my friends who I consider extremely smart. The thing crypto blockchain is still somewhat of a scam. What are your thoughts on?
I think some of it's a scam. I mean, look,
Scam.
trading gifts of monkeys for $300,000 was a scam. Okay, I don't think there's any way around that. On the other hand, money in general is just an idea, and it only exists because of it's like a collective hallucination, right? So, I mean, if Bitcoin is a scam, then the dollar is a scam, which arguably in some ways it is. And so, money is a scam. I mean, it's a scam, and it's also like the foundation of civilization. So it's a strange situation we're in. But much of our civilization is built on ideas, which are really rather hard to pin down. Like where do they exist? There's sort of a collective agreement or consensus or compromise. I mean, yeah, Bitcoin. I kind of think I see it in a balanced way. I mean, I see its features, but it arguably has some disadvantages or flaws compared with perhaps certain, as a store of value, it arguably has a certain disadvantages compared to, say, gold or something like this, because it is not only intangible in a sense, but it's not useful for anything other than being what it is. Like other stores of value presumably have value because they're valuable outside of just the outside of just being an instrument of I don't want to just say speculation, but they're useful for things in the physical world. Bitcoin isn't really directly useful for anything in the physical world, which is, maybe one might say that's an advantage of it. Maybe it's like a pure form of money in that sense. Well, I mean, I'm not an expert on Bitcoin, but I'm not like a Bitcoin booster. But I'm somewhat enthusiastic. I mean, I think it's a fundamental invention. It's also very interesting to me. You got to admit that the whole mystery of its creator sort of adds a dramatic element to it that it's hard to ignore.
Do you think it's the government that created Bitcoin?
Oh, I wish, kind of like they created Tor. Yeah, that would be an interesting twist. If they did, it would be one of the few times they were able to keep anything secret. No, yep. I don't think the government created Bitcoin. I think Bitcoin was created by a computer scientist, and I don't think they worked for the government. Although it's interesting speculation that perhaps they worked for the NSA or something like that. If so, they really kind of between that and Tor, they really kind of quote created a monster. Like they got all these drug markets and stuff like this going on. Yeah, I don't know how many different cryptocurrencies we need. The Ethereum concept is interesting from the point of view of a distributed computer. And smart contracts and stuff like that. I don't really know that it has any special value as yet another coin, nor do the hundreds of others. I know that they have little tweaks in this way and that, but I'm kind of a bit, as my friend Jessica said, I'm a Bitcoin monogamist.
Yeah, I think it's interesting because a lot of the Bitcoin community loves to separate themselves from crypto because they don't like that branding at all.
Well,
Understand.
that's like it's too late now, you know.
It's too late now.
I mean, they're not only it's not only they not Bitcoin has not only got the crypto brand, it's kind of got the crypto you know, national flag, right? I mean, it's like it's one would probably think it will be the last to go. It was the first to come and it will be the last to go. Um, yeah.
Yeah, one
It's
of the
not my field. It's really not my field. I'm just parroting what others have told me.
yeah, no, that's hey, we're allowed to have opinions. It's completely okay. Is there any way that you think, because I think one of the things that makes Bitcoin and sort of this sort of blockchain ecosystem very interesting is that it might open up a new path for funding in science. Are there ways in which you
Yeah,
think
yeah. I have a lot of friends who are interested in this DeSci, decentralized
DeFi
science.
precisely?
I don't know how well they're doing. I kind of, it's that's fine. Like, why not? Sure. I don't think it's gonna really rock the boat that much, except insofar as that perhaps something truly disruptive gets developed, with one of these projects. But it's not like look, the National Science Foundation has like, I don't know, probably close to $100 billion, or at least tens of billions of dollars. You know, the federal science research budgets, however misapplied they may be, are just so large that you're going to have some real DSI is going to have to bring some real advantages with it that make up for its lack of raw power. I don't
Yeah.
know. Maybe it will. I haven't tracked really my friends and their DSI projects. I know that if when I go back into the kind of heretical science funding that I want to do, I probably will not take the DSI route. I just want to go more the traditional VC route. Say like, look, I'm trying to raise 200 million. Check size is 20 million. Are you in? Right? If you want to call that DSI, you can. But it's not. Not. But I don't see what blockchain has to do with it. Like, if you want to contribute in Bitcoin, that's fine.
And the traditional VC way is pretty good. It's hard to argue against. It's hard to argue that there's a better system as of yet by any means. So okay, so to get back a little bit to some of your own history and some of your own work, you spent some time working for the International Space Sciences Organization.
Oh no, that was the organization that I headed that I talked to you about. Well, I
Okay.
didn't director of R&D, and I was that was the thing that did the heretical physics stuff back in the late
Right.
90s,
No.
2000s.
Right. No, I was just going to build on that. And then you moved from there into a research position, NASA Ames, and began doing large data simulation. Um,
No, actually, I was at NASA doing computer stuff. Then I took a sabbatical, did ISSO for a couple of years, then went back to NASA when ISSO ran out of money.
yeah.
And not because we spent it, but because our one angel funder uh, made some very bad decisions and spent all his money on stupid projects in my mind. And so ran out of money. So we had to close up shop. Um, and then, yeah, no, it was just a sabbatical basically.
Right. But then you came back to NASA and began working on data visualization, right?
Yeah, I was working on it somewhat before, and then I worked on it more, and I worked on all those things, optics, space missions, various things. And then went to Planet Labs.
Interesting. And you said optics. What does a computer scientist do at NASA in regards to
Well,
optics?
I had become more of a physicist, an applied physicist over the years, so I was not really more doing computer science per se anymore. Optics, it's another thing which you can do really high quality numerical simulations of optical systems, and you can optimize them and design them uh, to a large extent digitally, and then decide what to actually build after you've done created what seems like an optimal design virtually. And so that was the kind of stuff I worked on: telescopes, power beaming, um, that sort of thing. And then that led me to working on payloads at Planet Labs. So I designed a number of optical payloads, one of which is about to fly
You just
soon.
interestingly, you just casually dropped in power beaming, which I find, I don't know if that's like, is that something that's available at scale right now? What's power beaming?
No, it's not available at scale. Power beaming, well, any like laser communication system is essentially, if it's free space, not a fiber optic system, is essentially a power beaming system. You can beam power with light, with infrared light, with millimeter waves, even with microwaves, if you were willing to use large enough antennas. And there's been a lot of work over the decades on this. One of the driving goals, which is not mine, is directed energy weapons. I didn't work on those. Another driving goal is solar power satellites beaming energy collected photovoltaically and then converted into electromagnetic beams sent to the Earth. I'm not really active in that at all. I'm a little bit skeptical. Those numbers don't add up to me, with one exception, which I can't talk about, and which might actually work. And then I was working for a while at NASA on a friend of mine's brainchild project, Dr. Kevin Parkin's project, which was a millimeter wave beamed energy launch system where you'd use a high power millimeter wave sources on the ground with big antennas to beam to a launch vehicle, which would receive this power and use it to heat up propellant rather than using chemical reactions to heat up a propellant. The advantage there is you can actually put more energy into the propellant, in theory, using external power beams than you can using chemical reactions. And the energy you put into the propellant determines the efficiency of the rocket, basically, and the payload fraction. And so we did some work on that for a number of years, did some prototypes. And he's now working on another power beaming project for the Breakthrough Foundation.
Wow, interesting. I find power beaming just like one of those things that is inevitable in some sense. I feel like our iPhones will be charged by these satellites that beam down power at some point.
Our iPhones are already charged using near field charging, like with those
Wireless.
wireless. Yeah, but that's all near field stuff, which is calling that beaming is not really correct. There's no beam that's formed. It's just more like a transformer with the primary on one place and the secondary on the phone.
You think that far field?
What?
You think we'll get power beaming from satellites on iPhones?
No, no, I don't, because the problem with beaming power from a satellite to an iPhone is that it's going to go through your head on the way, and that's not probably wise. There's a chance, if one of these solar power satellite system works, that the power will beam from satellites down to receivers on the Earth in remote locations, and then the electricity will charge your iPhone the good old-fashioned way. So in that sense, it would be charged by power beaming. But no, I don't think we're going to have power beaming inside the home or anything like that. It seems like it'll have a lot of hurdles technically, and probably health physics hurdles as well, I'd guess. We're
That's
already beaming enough power into our ears when we hold our phones up to our face, So
that's a bit.
with our Wi-Fi, we've got all this power beaming going on that hopefully is safe. I mean, who knows?
That's a bit of a bummer. I was hoping that would work out.
Well,
Okay. Well, so then you leave and you join Planet Labs,
yeah.
which is a very interesting company. Do you mind explaining what the goal of the company is?
Yes, the goal of the company is essentially to sell data about the Earth that we gather from our fleet of about 200 Earth observation satellites. To anyone who's interested, our customers are mostly agricultural customers, insurance customers, government customers, both national security and civilian agencies, science customers, people working on ecology and anything having to do with earth science.
Are you open to independent researchers? Just
Of
like,
course, we have hundreds and hundreds of customers who are independent researchers. I mean, and we have university researchers, government researchers, we have plenty of customers that are companies that then do other things with our data and sell them further, do value add things or maybe combine it with ground-based data. Mapping companies, disaster relief, NGOs. Basically, our idea is we want to be kind of the source of truth for what's going on the earth. And so that people can't lie about what they're doing.
pretty noble goal.
Yeah. And so, there's various people with sub agendas at the company. Some people are really into the climate change narrative. Others are into national security stuff. Others are into science. I'm into all of it to some extent, except my primary passion is regenerative agriculture. So I'm really looking right now as to how we can use our data to enable global scalability of regenerative agricultural practices to save the soil or regenerate the soil, create nutritious food, biodiversity, sustainable farm economies, wean our dependence on capital-intensive, destructive external inputs like fertilizers and pesticides, and improve animal welfare. All these different things can all be kind of simultaneously optimized using regenerative agriculture, but it's complicated. And so one of the things that can help is remote sensing from space. It's by no means the primary lever, but it's the one that I have access to.
And how many satellites do you guys have up right now?
We've launched over 500, but we tend to only have them up there for a couple of years because we keep replacing them with better ones. So right now we have around 200 in orbit.
And do you guys use, do you send your payload up with through SpaceX or?
We in the past have sent our payloads up with practically everybody. We used to launch with the Russians a lot back when we were much friendlier with the Russians. We've been launching satellites for like 11 or 12 years. We used to launch with the Russians a lot. We've launched with all the American launch companies. We've launched with Rocket Lab from New Zealand. We've launched, I think, once with the Japanese. We've launched with the Europeans a few times. We're not allowed to launch with the Chinese. We launched with the Indians a bunch of times. They have a really good rocket that was quite competitive. But recently, SpaceX, the last couple of years, SpaceX has really dominated the market, and their prices are so much lower than others that we've been pretty much exclusively launching with SpaceX for the last 2 years.
Right. And how big is the company now?
Oh, we still occasionally launch with Rocket Lab. How big is the planet?
Yeah, how big is the
planet? Planet is close to 1,000 people, I think.
Oh, wow. And
Yeah, we have a office. We're an international company, headquartered in San Francisco, fairly big office in Berlin, and then Washington, D.C., and various smaller satellite offices in other places. And then, yeah.
And what was the size of the founding team?
Oh, the founding team. Well, I mean, there were 3 official co-founders of the company, 2 who are still active. There were probably, I'm guessing, 7 or 8 people who together completed the first satellite, or first two satellites that we launched, got them, you know, commissioned in orbit and got the first images down. But then it was like, that sort of proved that we could do it. And then additional people started coming to the company. I didn't join that. I think I might be like employee 40 something. I'm not exactly sure. That might be wrong about that.
And what are the differences in the working atmosphere in Planet versus in NASA? Is it
Well, I mean, to be frank, and I mean, I love Planet. It's my friends and family and my life, but as we get bigger and bigger, we get more and more like NASA. I mean, that's unavoidable. As you become larger, you become more organizationally, you get more layers to the organization, and you have to, like when we were a tiny little company in garage, you know, we didn't have to worry about so many regulations and da da da. Now we're a publicly traded company on the New York Stock Exchange, and like there's, you know, legal teams and HR teams and compliance teams and regulatory teams and, you know, security teams, and like you have to have all this stuff. There's just no way around it. But Planet is fantastic. It is a company. It's got great people. It's got a great mission. You know, the work is really fun. The work is meaningful. The people are talented and interesting. And you know, to work at a place where pretty much everyone is happy to be there and is willing to work hard to accomplish something together, that's like one of the greatest gifts you can have in life.
that's very, very true. It's hard to come by any place where that exists. And just to get back to sort of the satellites, what's the resolution on them? Can they see like a car very clearly from space, or what's their
We have, at the present time, and this will be changing very soon, we have two families of satellites in orbit. We have about 180, I think, roughly speaking, and they cannot see a car clearly, but they can usually see, you can usually have a pretty good guess that you're seeing a car on a road or in a parking lot. You might not be able to count the number, but you know, you can kind of tell like that's probably a car because it's on a road and it's like moving, and you know, we have a whole bunch of satellites that can see that, and we monitor the whole landmass of the Earth every day with those satellites. And then we have about 20 satellites in orbit that can see a car very clearly, like they can see the windshield and the color of the car and all this kind of stuff.
Wow. And so in some sense, the idea is to map out sort of this chain of images over the course of multiple days. How frequently do you guys take pictures
We
of
take
what's
pictures every day of all the land area of the world. Of course, a lot of that is covered by clouds, so we don't get a clear image of everywhere every day. Hang on a second, just to pause here. Is that we have a daily. So the idea is that we have a daily monitoring constellation that tries to image the whole Earth every day, the land and the territorial waters of all nations, and some other places. But because of meteorological conditions, sometimes it's just not clear. And then, you know, and then we have this, and so they're like orbiting and always kind of looking down, straight down pretty much. And then we have this other constellation of larger satellites, higher resolution, but smaller in number. And they do targeted observations. Like every day they're told where to look. And that depends on what our customers want and what we want. And so they don't monitor by any means everything every day, but they like monitor airports and ports and cities and, you know, certain areas that like maybe military is interested in looking at, or you know, where something happens, like if there's a disaster, we'll zoom in. So that's the basic method of operation. And you know, we do have a system now where we can use the monitoring constellation to detect changes, and then if something changes that's deemed interesting, either with AI or with a human, then it can task one of the high-res satellites to look what actually happened. So that's a thing that actually we're like the only company that does that, because we're the only company that has these kind of two families of satellites in orbit, as far as I know. Although I think governments do that as well. And then we're about to launch another two different classes of satellites, start launching them. One is an even higher resolution satellite to kind of replace the current crop of high resolution satellites. That'll take several years to phase one out and phase the other in. And then we're also launching some what are called hyperspectral satellites that are going to do another kind of observation.
Right. What is hyperspectral observations? Like what type of imaging is that?
Oh,
Is
that's
that
lower resolution in terms of the size of the pixels, but instead of imaging in like 8 spectral bands like we do now, these will image in like 500 spectral bands, so they can tell you very detailed information about the composition of what they're looking at, and they can tell you stuff about which minerals are on the ground or which gases are being emitted, um, that kind of thing.
interesting? So it makes a lot of sense to me that you're as interested about agriculture as you are, because I can imagine that this would be extremely useful in sort of understanding patterns and then finding ways in which to alleviate some of the concerns that someone might have. So do you guys give this to like the farmers and like
Anybody who's willing to pay for it,
anyone who's yeah,
pretty much, unless they're
right.
from North Korea or something like that, yeah. I mean, I don't know that we sell much directly to farmers. I wish we did. We sell to agriculture companies and other companies that then sell to farmers. Like they make specific products for farmers. Like they may take our data and turn it into information about pasture land and where you should move your dairy cows that day. That's not something we do. We can't kind of do specialized projects for we can't really do specialized products for all these different vertical markets, which are hundreds of them. So we rely on, to a large extent, on partner companies to take our data, partner companies that specialize in certain markets, like dairy farmers or corn farmers or, vegetable farmers or mapping companies or insurance companies. Like, what does an insurance company want to know? They want to know if like the homeowner has trimmed the brush away from their house so that they're compliant with their fire suppression commitments. We're not going to do all that. So they look at the data and they figure it out, and then they do whatever they do with it.
Why isn't there, or maybe this already exists, why don't you guys have like an app that like an average consumer like myself can just get on? And perhaps I don't get the same fidelity that someone else would get, but
We do have an app. It's not a mobile app. We have a web app called Planet Explorer, and you can go on it and you can look around. And you can probably even sign up for a free account and get a certain amount of free imagery. I'm not exactly sure what the status of that is right now. It's our main users access through APIs, but we do have this sort of web front end that people can dabble with. And why don't we have such an app? Well, let's see. Yeah, I don't really want to get into the company internal politics about such an app. I think that we have a revenue model that doesn't quite know how to justify supporting such an app, because we make our money by selling like hundreds of thousands of square kilometers, and most people are not going to be screwing around on their phones and doing that sort of thing. And everyone wants to see a picture of their backyard, but it's like that would be a nice thing to do. And if we were Google and had infinite money, we would do it.
makes sense. Makes complete sense. So just to circle back a little bit to some of your thoughts on what you termed earlier as heretical science. So we talked a little bit about climate change, and perhaps Planet can help. And do you guys, I mean, I'm guessing because you get a bunch of cloud cover sometimes, do do your satellites help in sort of modeling climate change in any way?
Well, modeling climate change, no, we don't model anything really. I
Okay.
mean, not in that way. Like climate models are a whole other topic and something that I don't have very much positive personally to say about, but be that as it may, not really my field. But I will say this, we have lots of people at our company who are concerned about climate change, although our CEO, who's very smart, to his credit, has for years now been saying something which I totally agree with. He and I may disagree on the edges on climate, but he says biodiversity is what we have to be concerned about and habitat loss. And like, if you fix biodiversity, climate will take care of itself. And so I'm in total agreement on that. It's one of the reasons I'm so into regenerative agriculture. But we do a lot with monitoring habitat loss and habitat restoration, deforestation and reforestation. And now with our new hyperspectral satellites, we'll be able to monitor gross polluters in terms of methane and CO2. So that's exciting. So we're not into modeling, we're into monitoring. We're
Do people
interested.
do people use your images for modeling in terms
Uh,
of
well, not. I don't think our images feed any global climate models. There are satellites that do that are like precision satellites that monitor temperature and
uh,
ocean swells and various global circulation of gases. Our satellites that are carbon mapper, which will monitor gases, it monitors like point source polluters. It can't really tell like traced amounts drifting between the continents, but it can definitely tell if some, gas storage facility springs a leak. Like it'll see that pretty much right away. So, if you're super concerned about methane and CO2, we'll be able to tell you some stuff, specifically if you want to monitor certain locations. If you're concerned about biodiversity, we can tell you stuff. If you're concerned about land use, like for instance, there's a lot of a number of richer countries are paying poorer countries to not cut down their forests. Now, this is, arguably a good thing to do, but there's an incentive, one might think, for some of these places to claim they're not cutting down their forests, get the money, and then cut down their forests and get the money for that as well. And so one of the things we're doing or helping to do is to make sure that, people are fulfilling their obligations under these agreements. And then there's plenty of similar stuff like, we can make other use cases, but so we are very much concerned with, although not exclusively focused on, ecosystem health and stuff like that. To the extent that climate is not a part of that, people's opinions may differ. To the extent that, but we don't really feed global models on
yeah, I guess you guys
classic climate things. Classic climate models, no. We might be, for all I know, feeding global models on that have to do with land use, land cover. I think we are. And another thing that I would say about that is that I'm very excited about something we haven't really done very much in it yet, but I think we may be able to, and it may be very interesting. No, actually, this is not true. We are doing, I forgot we have a whole set of products on this. It's a relatively new set. Hydrology turns out to be really important. Like, it turns out if you want to fix climate, you fix biodiversity and you get carbon and climate for free. If you want to fix biodiversity, you fix hydrology. And what that means is, remember that stuff I was showing you with the washes and this is the problem. The problem is that in much of the landscape in the planet, including in the US and the Southwest, particularly, it's desert. It wasn't always desert. Back when the conquistadors first came to Arizona and New Mexico, the grass was so high that they couldn't even see each other riding on horseback if they got separated. Now it's all desert. We can discuss why that is. It's not fossil fuels, I can tell you that. It's because of disruption of the massive herds of buffalo and stuff like this, to first approximation, and or disruption, extermination, and then mistakes about grazing. But the problem is when things are desertified, it's a vicious cycle, because once you start to lose vegetation, now when it rains, the water just runs off the landscape and erodes it. It doesn't get trapped. It doesn't feed the plants. It doesn't feed the animals. It doesn't make ponds. It doesn't make healthy soil. And then the land gets further desertified, and this process just gets worse and worse. Now, there are interventions you can do. You can build giant dams and stuff like this, or you can build like tiny little dams, and then maybe the beavers come back and build more of them. And once you've got tiny dams and little ponds, now the water stays on the landscape. Once the water stays on the landscape for a few days, it percolates into the groundwater instead of just running off into the ocean. And then once the aquifers start to get restored, and the soil gets restored, and the biodiversity gets restored, and now that actually cools the desert so that it gets more precipitation. And so you can boot up these virtuous cycles of ecological restoration that kind of, at the base level, to some extent, rely upon topographic and hydrological interventions rather than quote unquote planting trees, or sequester, or last thing you want to do is like cover it all with solar panels, I'll tell you that. But I'm really looking forward to how we can help with this, because we can monitor subtle changes in the elevation and topography and hydrology and soil moisture. And I feel that if we can keep good track of what's going on, we can really do our part to help reverse the desertification. I mean, the actual work has to happen on the ground. It doesn't happen in space, right? But the question is, are the interventions doing any good? And so I'm really hoping we can help provide reliable information on whether they are or not.
I think that's amazing. And I think that's part of the reason why I find that so many people are so excited about Planet Labs and what you guys are doing down there. Very, very excited, as am I myself. I think one of the other things that I find so interesting that you're involved in is the Galileo project.
Yeah.
Why did you join the Galileo project? What's your interest in that? And what's the point?
Well, I mean, you can read. I can't say that much about the Galileo project because not that it's secret, it's all open source and everything, but this is like, I kind of have to respect the director's wishes on this to sort of control the PR. So look, there's a little information looking down to the
Oops.
so what do we see? And so did you get that, or did we drop out?
No, we dropped out for a little bit.
Oh, what I was going to say is one of the reasons I'm involved in the Galileo project is as a representative of Planet Labs, because they're very interested and are currently using our satellite data to look down at the Earth and see if they see anything anomalous and moving above the clouds. And so, we're working on it. Let's just put it that way. It's nothing to write home about yet, but we'll see. And then because most of this stuff is ground-based observations, which is interesting, and I pay attention to it, but I'm not directly involved. And then I mean, like, I appreciate what they're doing. They're doing an open source, open data, kind of replicatable approach to looking for anomalous aerial phenomena. And I don't know what we're going to find, but whatever we find, unlike so much of the UAP chatter that goes on in our world today, this is all going to be like unclassified, open source. That's the approach. So that's what's cool about Galileo.
That's awesome. And I think it gives a lot of credence to it to see people like you involved because
Well, I'm
I,
not that involved, frankly, but I'm somewhat involved.
somewhat tangentially involved. Yeah, I don't know. The whole UAP UFO conversation is somewhat mind-numbing to an extent. But
Yeah, yeah. And because of the fact that there's so much confusion and so much unverifiable claims and so much like
ambiguity.
ambiguity and sort of confusion isn't exactly the right word, but let's just call it confusion because it edges into like apparently classified domains. Like this is one of the reasons for the Galileo project is to bring some sanity and transparency to this kind of investigation and some scientific rigor.
Keyword sanity. Yes, I think this has been amazing. One of the last questions that I love to ask everyone that I interview is what in your mind is the most valuable idea on planet Earth at this moment in time?
Freedom of speech.
Ooh, ooh, very
and the concomitant freedom of thought and freedom to discuss and freedom to debate and freedom to problem solve as a group. Because if you don't have freedom of speech, this is like basically Jordan Peterson. But if you don't have freedom of speech, you can't do any of those things. You can't actually debate. You can't actually collectively solve problems if you will not tolerate dissenting opinions.
I think that's as good as it gets. I think that's extremely important as well. And with that, I'd like to say, Mr. Creon Levit, this has been extremely, extremely interesting for me. It's been an honor to sit with you. Thank you for gracing me with your time. And there's this humility that emanates from you that I didn't think I would see. I am honored to be amongst it, and thank you for joining me again.
All right, you're very welcome, and good luck with everything.